Okay. Like Dr. Ledger said, we're the CPOD drone dispensing team. I'm Adam Brewer, Trevor Gressel.
I'm Donna from Children.
Justin Clark.
Lana Schulte. So the goal of this project is to create a cost-effective drone with a seed dispensing mechanism to improve our reforestation effort, not only here in the US, but all over the world.
Here is some of the state-of-the-art designs that are currently out here. This first company, Biocarbon, uses a shooting mechanism and a ball dispenser similar to a paintball gun. They also use foldable wings, and they have a detachable system. They are a more rugged and more expensive company. They use an 8-motor system to fly their drone. The next company is Drone Cora. They went with a more eco-friendly 6-blade design. They're using all CNC machined and laser cut wood pieces, and their dropping mechanism focuses on dropping all the seeds at once in one area to increase the overall germination rate for that spot.
So a little overview on the shape of our project right now is we are essentially made up of 3 different teams. We have ourselves, who are in charge of the drone body design, the dispensing design, the weight of the drone, and decisions made on motors, propellers, and ESCs. And then we also have in our group a couple of electrical engineers that are in charge of our electronic choices, flight mapping, and the autonomy side, as well as some remote controllability. And then we also have our CPOD manufacturing team that we work pretty closely with as they give us the CPOD dimensions, the weight, and the contents of what we're dropping. So our final goal is to make an open source so anyone around the world can look it up online and find drawings and components and work themselves.
So with that, this is part of what the EEs are doing, which is essentially flight mapping. And what it does is the drone, you get a satellite image, it goes up, it draws a flight path, and then it creates these points. And at each one of these points is where the drone actually dispenses the seed. And you can see this is up top is kind of what we think the flight path will look like. And that's actually the lot just outside of your colors. And basically the drone goes up, it goes down, it goes back and forth, and then it goes back up and moves back around and comes back to its home position, while dropping seeds along the way.
So this is what our CPOD manufacturing team is working on a little bit. So we are basing our models based off of a 1.25 diameter sphere. So this is just the ball that they're planning to use with tree seeds inside, and it will be packed with nutrients as well. Their presentation is 2 after us, so stay and watch.
So another thing, some of the main goals, a little bit more in depth of what we're specifically trying to hit. We are required for the drone body, as stated before, the seed dispenser and hopper, and also the motor, props, and the electronic speed controllers that actually help control the motors themselves on the drone. The drone body, one thing we wanted was it obviously to be made out of lightweight, durable, but one of the biggest things was readily accessible materials, which then adds a little bit more complication to the project, but we will explain that later. The seed pod dispenser obviously needs to be able to drop seeds upon command from the flight map that I showed you earlier at those points. So that means it's probably driven by some type of motor that then the EEs have in their code to then drop the seed pod when needed. They also, and then quite obviously the motors, the props, and the electronic speed controllers need to be able to support the size of the drone that is being built.
All right, these are some of our objectives. Some of them are our sponsors / our objectives. Some are FAA regulations. We want to be able to do about 200 seeds per acre, and our flight time, we're shooting for 1 acre, so we need our battery charge to be able to cover 1 acre. And I think we'll go into batteries a little bit later. And then the FAA regulations that we have to follow. Our drone cannot be more than 55 pounds, and that's takeoff weight. So that's drone, seed pods, dispensing mechanism, everything when it takes off can't be over 55 pounds. We have a 400-foot altitude limit. We're not planning to go anywhere near that, but that is the limit. There's also a line of sight limit, so we can't fly blind with it. And then we want to want to be able to do it throughout the world, so off the shelf parts as much as we can. Like Landon said, it's gonna be open source, we'll have bill of materials, all our coding will be online. Flight instructions, assembly instructions, all that stuff's gonna be free online, so whoever wants to be able to download it, build it, and use it, can.
So when we looked into constructing our drone, first thing we had to figure out was the material for the drone. So when we researched, we came up with 3 materials, PVC, plywood, and carbon fiber. And so we looked at those materials individually to figure out what would be the best for our drone. So when we looked at carbon fiber, although carbon fiber provides the optimal weight and durability, but it's far too expensive, it's not easy to work with, and it's not readily available everywhere. So the next material we went with was plywood. Although plywood is available most of the places, but it's very hard to work with when you are thinking about constructing a drone with it, because you need special equipment like CNC router, and it's pretty heavy, so we would not be able to meet our 55 pounds constraint. So the last material we looked at was PVC. PVC is available worldwide, it's cheap, it's easy to fabricate using the basic tools, so it has an easy build system, and it's lightweight. But one of our concerns was whether PVC would provide us with the correct flexibility / rigidity.
With these concerns in mind, we decided to do some first semester testing on PVC's different abilities at different weights. So we went ahead and decided to build an apparatus that would simulate the motor and weight that our arms would experience on this drone. Seen at the top is our undeflected model, and then we have 2 more deflections. This first side is 3/4 inch PVC, and then the far left side is 1.25 inch PVC.
So after we completed our testing, we got our results and put them in an Excel spreadsheet. And in order to determine what kind of PVC would be best for our drone body, we made 2 graphs, a load versus deflection graph and a stress versus strain graph. So in the load versus deflection graph, it's how much load you're applying and how much deflection you're getting from the PVC. And over here, as you can see, the blue color represents the 1.25 PVC. The orange color represents the 1 inch PVC, and the gray represents the 3/4 PVC. So as you can see from the load versus deflection graph, the 1.25 has the least deflection with a lot of load applied as compared to our 1 inch or 3/4. So the next graph is the stress versus strain graph. So stress versus strain graph is just telling you how strong the material is, and in this case, the higher the slope, the steeper the slope, the stronger the material. So as you can see from our graph right here, the 1.25 inch has the steepest slope, it gives a maximum strength. So what we decided on was to use the 1.25 inch PVC to construct our drone body, but the 3/4 and 1 inch PVC can also be used for the less force intensive purposes, for example, constructing the hopper or anything down there. You'll see the future slides.
So this is how we essentially picked out the motor, and obviously there's a lot of data that goes behind motors, but there's 2 main things that you want to look at when finding, that's thrust and power. So the website we used was called Mad Motors, and there was obviously almost overwhelming at first how many motors were available, and none of them were quite 100% sure on actually how to spec them out. So to help with this, we made a spreadsheet, and this Excel spreadsheet has essentially every motor available that's on their website. And from there, you can then obviously filter and sort and get the motors that you want based on thrust and power provided. And so that led us to finding this current motor that we are planning on using, the MAD 8112, which provides us plenty of thrust for what we need. And it also has the lowest power consumed that we could find. So we're trying to save on that battery and hopefully hit that 1 amp arc that we were talking about earlier.
So this is our drone body concept design. It's made out of 1.25 inch PVC throughout, and then those parts you see drop down at 1 inch. It's about 66 inches long, so it's about as tall as me, just slightly turning. And then the orange base, brown base in the middle is plywood, so that's where we can mount electronics and anything that needs to be mounted up there. The battery mounts are still a concern as to where those will go, but that is important.
So these are the motor mounts that we currently have, and that's again based off of the MAD 8112 motor that was found previously. And basically, this is just it has two halves that come together on the end of the pipe, they clamp together. And then with these holes right here on top, then the bolts, you can run bolts through the PVC pipe and then hopefully have it so you also have the clamping force and you also have it so hopefully it doesn't move with bolts running through it. And then with this as well, you have the slots and that's where your bolts attach to your motor, so it goes underneath and screws in. And then we also left those openings on the bottom there as well, because we're thinking maybe we could then run the wire from the motor into that, and then there's a cutout in there, which then you could run your wires through your PVC, to hopefully then give them a bit more protection from whatever elements that you might be in. But you can see that they're honestly pretty large, 8.5 inches long and 2.25 inches tall, but it should hopefully provide us plenty of support for the large size drill that we're trying to build.
So, like we mentioned, that one of the biggest constraints you're working with is a 55-pound weight limit. So, what we came up with for a hopper design for that, instead of using plywood to create a hopper that would just add weight, and instead of 3D printing the whole hopper system, we came up with this design. So, the red portion is nylon. It's a pretty lightweight material, and it runs from the top of the hopper. As you can see here, it's wrapped around the top, and it goes down, and it's wrapped around the bottom. So this creates a funnel which would direct the seeds into the next part of the process of seed dispensing. And all whole hopper system, it has a 22-inch base and is 12 inches long.
So this is the funnel that's gonna go from the hopper and get us down to the 1.25 PVC that we're using for our tubing. Essentially, we are constrained a little bit by PVC joints that we're using. So we won't be able to get the nylon hopper all the way down to the 1.25 piping that we're using. So we're gonna 3D print this funnel device. Right now it's 9.5 inches wide, square. It's gonna fit right on the bottom of the funnel or the hopper, that previous slide. This design is about 6 inches tall. It's easily customizable, so we're gonna print one, do testing on it, and if we run into issues with the seed pods jamming in there, we can increase the height, hopefully prevent that. And then it'll funnel it down to the 1.25 pipe that will only allow one seed at a time to pass through it, so we won't run into issues of multiple seeds dropping. We only want one at a time.
So this is a design for a dispensing mechanism, and it's based off of what you might see in a gumball dispenser. And basically, it's just a rotating plate around a track that essentially one ball would drop from the funnel down into one of the slots, rotate around as other balls are continually dropping into each slot and falling out on the 90-degree gap there on the bottom of the track. It's essentially a pretty simple design. It can be run with one low RPM DC motor, and it allows for variation in speed of the dome quite easily for drop rates.
And this is our full assembly, so all of that combined, sits at about 23 inches tall. And again, 66 from wing to wing, but up there at 24 to 4. We are proposing the idea of adding wire in between the arms to add some rigidity if it's needed, as that is a very lightweight material to use. That's about it. You can see all the different components that are color coded on it.
So we're also, one of our objectives for reach goals was to make it detachable and take it apart and reassemble it if need be. So in this situation, we try to get detachable arms so you could walk it through a small door or something like that. Make it more movable and just easier to get around somewhere.
We also plan on having the upper drone body be able to detach. This is simply for transport and ease of working on different components. We will also be PVC cementing the bottom portion to be more rigid. But we're hoping to be able to separate it as drone body and hopper system as well.
So for our budget, we started with a $3,000 budget, and of course, we're building a 55-pound drone essentially, so motors are kind of big and kind of expensive, props as well, ESC as well. And so most of our electronics, battery motors, stuff, took a lot of our budget, so we were kind of constricted with cheaper materials. Anything we could find for, that would work, that might not be something that everybody wishes they could do. That's basically what we're working with, and right now we're sitting at $360 over budget, but we're hoping that we can at least stay there and not make it any worse.
And we've got the weight budget, so obviously we're trying to keep it under 55 pounds. So we've got our seed pods estimated at 14 pounds. Those are kind of subject to change depending on the manufacturing group. Our batteries are taking up a lot of that weight, there's almost 13 pounds there. Overall, we're sitting under budget, which is a relief to us that we can add some more rigidity elements if we need them.
This is our Gantt chart, and it's mainly going forward. Right now, we're in the process of just kind of finalizing all of our models on the computer. We still need to input the electronic devices in our models. That's kind of an ongoing process. And then basically testing is what we have our main focus on. We've started some, like we talked about, the PVC testing to just make sure that was a viable option for our drone body. Going forward, our hopper testing and dispenser testing is what we're going to start next. Want to make sure that we're not going to run into any jamming issues. So if we need to change pitch angles on our hopper or our funnel, we can do that. And then we'll have our flight and battery testing next semester, and then hopefully a final assembly by the end of next semester.
Thank you for listening to us. Are there any questions?
Your detachable like hopper and would you have concerns of it coming loose potentially? It's like if you're going up and
Planning
down.
on using bolts.
Oh, you
Bolts or pins or something to hold them in there.
Sure. What's your follow-up question? What's like a time frame to like properly disperse your seeds over an acre? Do you have a time frame?
We did some calculations with the dispensing mechanism, and and you're running the drone at 2 miles an hour based on our total distance of flight path. It would take about 16 minutes, and so that drops down somewhere around 16, I want to say, minutes. And at 8 miles an hour, it was not that hard. Five. And I've never just multiplied on it.
So what height do you plan on operating it at? And how precise is that gonna be?
For our flight height, we're thinking more like 5 meters. So it wasn't too high. We're gonna try and stay below like tree height. Ideally, it's gonna be like on the field where we're expensive these, so we don't have to worry about running into trees and stuff. Yeah, plan on about 5 meters, and precision is a huge factor for us because you know how many times you go to a forest by perfectly aligned rows and trees. So it's good, we're gonna drop it at set intervals, but if it's not perfect, it's not a huge deal for us.
What's the largest like payload you guys could carry?
That will slightly depend on the battery usage as well, so right now, if we like to wait, we could increase, but if we carry more seeds, then the goal is to go for another acre, so then it's kind of dependent on that. This 14 pounds is also slightly oversized from what the actual seed pods are looking like they will weigh, so we're adding in a little buffer rooms.
It's about a factor 2 of what we're budgeting for our seed pod right now.
Is there any wind and temperature, things you need to be concerned about or limitations that you have to watch for, or haven't you figured that yet?
Yeah, so that's gonna be more on the electrical side. They have with their flight control and stuff. Their cube.
Yeah, so
takes
their
into account
cube
for
can
movement.
only run in very minimal winds, close to 12 mile an hour, less than 12 mile an hour winds. So we're hoping it's not with the wind.
Basically ideal temperature and. Wind, weather conditions, no precipitation.
Nobody wants to be out when it's bad time, bad weather out anyways.
What time of the year are you? Thinking some nut trees and stuff like that can be planted in the fall, and then other smaller street trees such as pine and stuff like that, planted in the spring, so. May, June, or September, whatever. So.
Yes, I got two questions. The trajectory of the seed, I mean, the electrical engineering people are gonna figure the projectile motion for that seed, so. Or isn't that a main concern then?
Not a main concern. Like I said, our accuracy is a huge priority as long as we're, getting that coverage of the whole acre, so. Ideally, we're gonna drop as we fly, so we don't have to stop and start and waste battery on that sort of thing, so. It's depending on how fast we're flying, it kind of depends on how, and your height, depending on how early you want to drop to get in your zone, but like I said, our accuracy, our top priority.
And then just something to add on to that too, but we went out in SolidWorks, we made like an acre square and then split it up into 200, because our goal was 200 seats. We split it up into 200 even squares. And when we did that, each square ended up actually being fairly wide, and it would honestly be bigger than I thought. It was, yeah, it was like 13, 14 by 14.
So you got like 26 feet into each drop, so you got,
Did you have another question?
Yeah, then the other question was on your stress strain diagrams. So you went to the MTS machine and you got your stress strain based on bending, right? But when you calculated, I should say load deflection, you got your load deflection from the MTS machine, but then when you calculated your stress, how do you calculate the stress? Kind of curious.
The machine output stress as we applied a force load, so we just applied one load, and the test machine output stress.
I guess my question would that be bending stress or would that be tensile stress? I'm a little bit concerned, but ultimately you're concerned with the stress that's going to be on the arm, got the motor on there.
we did our test at full length of the motor, but with our hopper and everything, it's realistically not nearly that long. What our bending is gonna be, we'll have our T joints, and it's only like about 20 inches maybe from that T joint to the end of the motor, so it's not nearly as, we're kind of going worst case scenario there, so.
Quick thing to add, it's particularly the water side. So there's like joints here too, so when we did the testing, we did it with the worst case possible. And that's not including, like Adam said, not including any of the T joints, any of the supports that would come to help with the bending.
So basically the testing from there to there, putting 1.1
With
in,
no,
where realistically it's gonna be, it's this little section that's gonna take most of the bending portion.
Okay, with that, I think we have to move on to the next.